What the heck?
Tagon.
Hello, so this is going to be a response video to one of my personal favorite mathematics YouTube channels, BlackpenRedpen. He just came out with a video today doing a very interesting integral over the product of the cosine and the inverse cosine over the entire domain of the function in the real numbers. And it was very, very interesting how it came out to a very neat, simple answer, and I'm going to quickly review how to derive that answer in this video, but then I'm going to follow it up with the analogous integral over the product of sine and the inverse sine, and you end up with a very, very interesting answer, and so I wanted to cover that today quickly, just to see if I could sort of be part of the problem solving, because I love this kind of stuff. I love neat calculus questions. So let's get to it. I want to consider the integral from -1 to 1 of sine of x times inverse sine of x dx. Now, both sine of x and inverse sine of x are odd functions, and you'll find through a little bit of investigation that the product of odd functions is an even function, which means that since I'm taking this integral over a symmetric interval, I can actually rewrite this as 2 times the integral from 0 to 1 of the same product, right? So it's just now 2 times the integral from 0 to 1 of those two things. And we're going to make a very, very similar substitution as we did with the cosine product. We're going to let x equal the sine of t, which implies that dx is equal to cosine of t dt. And our new integral is 2 times the integral from 0 pi over 2. And this is sine of t times t, because the inverse sine and sine cancel, times the cosine of t dt. And now that we've done our substitution, we can do some integration by parts. So we're going to differentiate t, we get dt, and we're going to integrate the rest of the product. So we have sine of t times the cosine of t dt. Do simple integration u substitution, and you will get negative cosine of sine of t. And now we simply multiply through, and we get minus 2 times t times the cosine of the sine of t from 0 to pi over 2, minus the integral of their product, so minus minus gives plus 2 times the integral from 0 to pi over 2 of cosine of the sine of t dt. Okay, if we plug in pi over 2 into this, we get negative 2 times pi over 2, and that's negative pi. Sine of pi over 2 is 1, so we end up with cosine of 1 times negative pi. If you plug in 0, you'll see that we get 0 here in the product, and that goes away. So the first term, this thing evaluates to negative pi times the cosine of 1. And now, what I'm going to do is I'm going to consider this function here. We've derived that our original question, the integral from -1 to 1 of the sine of x times the inverse sine of x dx is equal to negative pi times the cosine of 1 plus 2 times the integral from 0 to pi over 2 of the cosine of the sine of t dt, right? So this is what we've shown so far, and I want to evaluate what this might be. So what we want to do is we want to show that this is actually even. So just think about it. If we plug in negative t, sine of negative t is the same as negative sine of t. But the cosine of something negative is the same as the cosine of something positive. So plugging in negative t for t gives the same function back, which means that this function, the integrand, is even. So 2 times the integral from 0 to pi over 2 is the same as the integral from negative pi over 2 to pi over 2. Simple as that. Now what we want to do is we simply want to plug in t equals negative pi over 2 minus u. When we get negative pi over 2, that must mean that u was 0. So we get an integral from 0, and then if we want it to be pi over 2, then this needs to be, u needs to be pi, so that pi over 2 minus pi gives negative pi over 2 times negative 1 gives positive pi over 2. So we get the integral from 0 to pi of the cosine of the sine of negative pi over 2 minus u. This is equal to we can just pull out that negative sign there, but then of course that goes away. And what this substitution gives us is we have now from 0 to pi cosine of u du. But think about it for a second. Cosine is an even function, which means if you plug in negative inputs, you get the same thing out as if you plug in positive inputs. And if we think about cosine from 0 to pi over 2, it takes on all of the values that sine does. We can draw it out a bit. So from 0 to pi, sine goes like this. And from 0 to pi, cosine goes like this. But because cosine is an even function, if I take the cosine of this graph here, we end up with some function. But if I take the cosine of this graph here, it's essentially the same as if I take the cosine of the absolute value of that graph, because the negative factor doesn't matter. But because this function hits all the same values exactly the same amount of times as this hits all of its values, and we're simply taking the cosine of all of them and adding them up together, you end up with the same thing. So even though this is the graph of sine, and this is the graph of the absolute value of the cosine, and I guess also technically absolute value of sine, even though it's already positive, this is no different than the integral from 0 to pi of the cosine of sine of u du, which is very important, because that means we can just immediately go back to this function here the way we had it. So what this is actually equal to in the end, what our integral is negative pi times the cosine of 1 plus the integral from 0 to pi of cosine of sine of t dt. But what the heck is this? We're going to rewrite this slightly. So what we're going to do first is we're going to factor pi out of both of these things. So we're going to end up with pi times the quantity, which is the integral from 0 to pi, times 1 over pi, by the way, because there's no factor of pi over here, so we have to factor pi out, so we have to multiply by 1 over pi. And I'm going to write this as the cosine of, and now you might find this weird, but just go with it, 0 times t minus 1 times sine of t dt minus cosine of 1. And this is a very particular way of writing this, because this is a special thing. If I consider these to be sort of arbitrary numbers, this 0 and negative 1 here, if these are just arbitrary numbers, then we have a special definition here. There's something called the Bessel function of the first kind. It's denoted j sub n of x, and it's equal to 1 over pi times the integral from 0 to pi of the cosine of n times t minus x times the sine of t dt. So take notice, if I plug in 0 for the n, this is 0 times t, and that goes away. If I plug in 1 for x, I get negative 1 times the sine of t, or negative sine of t. And negative sine of t, the cosine of negative sine of t, is the same thing as the cosine of sine of t. So this is a perfectly valid representation. And so these will all go away. So if I multiply the pi in, these two cancel. 0 times t is 0. This is negative sine of t. Cosine of negative sine of t is the same thing as cosine of sine of t. So you get right back to this integral up here. But because this is the definition of the Bessel functions of the first kind, or the second kind, I can't really remember which one it is, I think it's first or second, I can write this in terms of this function here. So this thing here is j sub 0 of 1. So the constant that the integral under the function sine of x times inverse sine of x from negative 1 to 1 is equal to pi times the 0th Bessel function at 1 minus the cosine of 1. So this is what the integral from negative 1 to 1 of the sine of x times the inverse sine of x dx is equal to, compared to the other one that BlackpenRedpen did, which was this, equals pi times the sine of 1. So that was what he showed, and this is what I'm showing in this. So based on the definition of the Bessel function that I just gave you, this is what this number is equal to, and it is about, what's it about equal to? It's about equal to 0.7-ish. Not a very large number, but it's about equal to that. I'm going to do my own explorations of these functions that are functions times their inverses, because I think it's really, really interesting. I've compiled like a list of all of the common functions that seem like they have any interesting intervals to take integrals over. And I'm going to try and do a few videos on those. So thank you very much for watching. This has been a pretty cool little exploration. I'm going to do another way of deriving this amount in a different video when I do my own exploration of these. So this is the one that BlackpenRedpen did, this is the one that I did. They're both very, very interesting, and thanks for watching.